this is the notes for section 2.7, fitting a model to data, part 1. This is our first look at actually modeling data, and it's going to be an overriding theme that we have throughout this entire course. But what we want to do is the following. We want to look first at what a mathematical model is, and it's just a description of a real-world situation using the language and concepts of mathematics. Generally, for this class, this will involve coming up with a function to model a situation. This right here is pretty much what we're going to be doing. In this lesson, we are looking for direct and inverse variation models. So the models that we're going to be working with here are models that are of this form: y equals kx, or y equals kx squared, are two direct models that we've looked at, or direct variation models I should say, and the other one is y equals k over x and y equals k over x squared. So those are the four models that we're going to be interested in as we try and model a set of data today. Alright, so here is the steps that we're going to use for creating a model for a variation equation or variation set of data. So to begin with, we're going to do a scatter plot of the graph, and I'm going to show you in a little bit how we can use Desmos, or you could use your graphing calculator as well to do that. Look at the shape of the graph to see which variation equation it fits. So we're going to be looking to see if it fits one of these four variation equations. Okay. Then we're going to set up a general variation equation that fits that data. We're going to plug in the data to solve for a general equation. Use the constant of variation in your general equation to come up with a specific equation, and then finally check your answer to make sure the data points work. So that's kind of the process that we're going to use to come up with our models here. Alright, so what I'd like to do is I'd like to do those steps in this particular example. So it says Susan measured how far a marble rolled down a ramp over a period of time. She obtained the following data, where t refers to the time in seconds and d refers to the distance in inches, and it's to find the equation that relates t and d. So here is the model that we're working, or here's the data that we want to model. Okay. Well, to begin with, what I'm going to do is I'm going to come over and I'm going to do a scatter plot, because that was our first step, is to do a scatter plot of the data. So what you might want to do right now is just pause the video and open a Desmos or open your graphing calculator. I'm going to do it in Desmos just for simplicity right now. Alright, so if you come over to Desmos here, I entered this equation in a table, and you can get a table by hitting the little plus sign here and come down and select table, and then you can just enter the values into your table. Now you can do the same thing on your graphing calculator, but really for something like this you might find that it's just plain easier right in Desmos. And then what I did is I adjusted my screen, so if you go to the wrench you can kind of change what your x and y values are, so you can see, hey, is this as I'm looking at this, and I'm going on to step 2 now, if I look at my graph, is it growing in a linear fashion? Is it making more of a parabola, more of a hyperbola? What type of a shape is it making? And if we take a look at it, it appears that it's not linear. It appears to be much more of a shape that would be, so it looks like parabolic. Okay, so if it's parabolic, what I would want to do is I want to think about, well, which one of these graphs here looks like a parabola, and we know that the answer to that is this graph right here. That's the one that's going to look like a parabola. So we want to do, so that was step 1 and step 2. So what we want to do is we want to set up a general equation that models that. So the general equation would be distance is equal to k, the constant of variation that we want to find, times t squared. So that's our general equation, and that is now at a setup so that we can find this constant of variation. So we're going to use the data to do that. So now what I'm going to do is I'm going to pick one of my data points to plug into my equation. So it really doesn't matter. I'm just going to go ahead and pick this first one right here, 1 and 0.6. So if I use that data point, I can plug that into my equation and see if I can come up with my constant of variation. So I can say 0.6 is equal to k times t squared, or 1 squared. Okay. Well, if I do that, 1 squared is 1, so really it's just k is equal to 0.6. So there's my constant of variation, which brings me to my next step where I'm going to rewrite this now with this k value plugged in for it. So I'm going to say d equals 0.6 t squared. Okay. Now, this is the general equation. This is the specific equation. It's specific because it now has a value for k in it. So we've now taken our way through this one, and this one. And then finally we can check our answers. So what we can do is we can plug these values in and see if they work in here. The other thing that we can do is if we write this as a function, we can see if how close our function matches the data points that we have over here in decimals. So if I come back over to decimals and if I add another line, and I'm going to put in f of x, okay, equals, and then I want to put in 0.6 x squared. And you'll notice that those points aren't exactly on the line, but they're very, very close. So it looks like we've come up with a pretty good model for our data. Alright, so what this tells me is this equation right here then would be the model for the data that we have above.